Galaxies in the local universe display a wide range of morphologies and a large diversity of stellar structures, as we can see on these images from the Hubble Space Telescope. We see bars, the smooth and elongated stellar structures that we often find in the central parts of galaxies, spiral arms which stretch from the center towards the outskirts and which can be more or less tightly wound, or rings, sometimes hidden at the heart of galaxies and other times located at further distances from the center. But let me briefly introduce PHANGS. PHANGS is the largest high-resolution survey of star-forming nearby galaxies, with a large program on ALMA, another one on MUSE, also the HST, and now also JWST, and provides us with a cloud-scale view of the star formation process. Our final goal is to try and understand the baryon life cycle in galaxies, from the condensation of diffuse atomic gas to form molecular clouds, their collapse to form stars, and the feedback processes associated with star formation. Specifically, since stars are born out of the dense molecular gas, we want to track the distribution of molecular gas across our targets. The most abundant molecule in the universe, molecular hydrogen, or H2, doesn't have a permanent dipole moment, and thus it cannot be easily observed under the typical conditions of the cold interstellar medium. That is why we use instead carbon monoxide, CO, the second most abundant molecule in the universe, which efficiently emits at millimeter wavelengths. And this is the emission that we are detecting with ALMA, producing maps like this one, not only for a single galaxy, but for a sample of around 100 nearby star-forming galaxies. In addition to tracking the distribution of molecular gas in our targets, in this study we are also interested in examining how efficiently that gas transforms into stars. And for that, we use maps of star formation rates, how many new stars are born per unit time and unit area. And for that aim, first of all, we use maps of H-alpha, emission that arises from hydrogen that gets ionized in the immediate surroundings of young newborn stars. But for most of this paper, we actually work at slightly lower resolution of about 1 kiloparsec, employing as a star formation tracers a combination of ultraviolet and mid-infrared emission, which accounts for both for obscured and unobscured star formation. As I already mentioned, the main goal of this paper is to identify how gas and star formation distribute across different environments, and for that we have built a set of environmental morphological masks for PHANGS that I'm going to present now. These masks contain, from photometric decompositions, bulges and disks, and from visual inspection and fitting, bars, spiral arms, rings, and lenses. These masks are publicly available through the PHANGS webpage, and in this paper, for simplicity, we reduced them to 5 simple environments: center, bar, spiral arms, interarms, and disks without prominent spirals. Let me show you an example to illustrate how we constructed these masks. We start from a near-infrared image, in this case from the Spitzer Space Telescope at a wavelength of 3.6 micron. On this image, we defined bars through visual inspection and ellipse fitting, following Herrera and Doki et al. 2015 for galaxies in the S4G survey, and other papers from the literature or new measurements for the remaining galaxies. Then we delimited lenses, which are often the rounder, thick structure associated with the central parts of bars, and we followed a similar procedure as for the identification of bars. For spiral arms, we started identifying strong peaks on an unsharp masked version of the near-infrared image, which enhances the brightness contrast associated with spirals. These spiral segments have then been fitted in polar coordinate as logarithmic spirals. Then these segments are dilated and assigned a width following an empirical criterion based on the recovery of CO flux. Like this, we have our final spiral mask. This also largely follows Herrera and Doki et al. 2015 for S4G with some modifications and new fits for all remaining galaxies. Rings are identified visually, while finally bulges and disks come from photometric decompositions with GALFIT. These are all additive components in the sense that they can overlap in space on top of each other. Let me show you another example to illustrate a little bit better these masks. This is the environmental mask for NGC 4321, where I have also identified the prominent bar lanes. This is what it looks like on top of the molecular gas distribution, and this is the result of overlaying it on top of the star formation rate map. Using these environmental masks for PHANGs, we have carried out a census of the distribution of gas and star formation across these different environments. The first column here shows the distribution in terms of area. For example, in this galaxy, the red part would count as center, the remaining green footprint would count as bar, the blue part would correspond to spiral arms, and the rest to interarm. When adding up the emission contained in these masks across all PHANGs targets, we see that centers take a tiny fraction of the area, while most of the area is covered by interarm and disks without strong spirals. However, in terms of molecular gas and star formation, they are quite evenly distributed across the environments. Now we are going to examine not only the total amount of gas and star formation, but how their surface densities distribute across environments, the mass per unit area. On these plots, I'm going to show the distribution of surface densities as a function of normalized radius. On the left, in logarithmic scale, molecular gas surface density as a function, also in logarithmic scale, of radius normalized by a reference radius, R25. On the right-hand side, the equivalent thing for star formation rate surface densities, also as a function of radius. This is the distribution of data points across all PHANGs galaxies. Each of these data points comes from an aperture of around 1 kiloparsec in size. And we see that centers stand out as the structures that host the largest amounts of molecular gas in a small area, the largest surface densities, and the same applies to star formation rates. Bars follow a diagonal line spanning a large range in radii and also surface densities. Disks without strong spirals significantly overlap with the outer parts of bars in terms of surface densities. The same applies to the values for the interarm, and spiral arms tend to have slightly higher surface densities at the same normalized radius. However, if we pay attention, we see that there is also a big overlap between spiral arm values and bar values, implying that for two different galaxies at the same normalized radius, we can find bar surface densities which are comparable to the surface densities that we find in spiral arms in another galaxy at a comparable normalized radius. The plots that we just saw make it clear that there are bulk offsets, bulk differences in terms of surface densities among some of these environments. For example, we can wonder if the centers of barred galaxies are different from the centers of unbarred galaxies. To tackle this question, we compute the ratio of the average surface densities in the centers of barred galaxies, like the example on your left, as opposed to the mean surface densities in the centers of unbarred galaxies, like the example on your right. Here we would take the mean values within the blue shaded area and divide them by the mean values in the gray area, including spiral arms and interarm regions. What we find is that the centers of barred galaxies have much higher molecular gas and star formation rate surface densities than galaxies without bars. Also, the distribution for barred galaxies is much wider. Bear in mind that this is in logarithmic scale, so surface densities in centers go up to 10 to the 3, 1,000 solar masses per parsec square, huge. Whereas for non-barred galaxies, the mean surface densities go up to at most around 10 solar masses per parsec square. Now we can actually combine these two pieces of information to try and understand if the centers of barred galaxies transform the available gas more efficiently into stars than unbarred galaxies. For that, we examine depletion times, which are the time that it would take to consume the currently available gas at the present star formation rate, if this star formation rate were sustained over time. Short depletion times imply an efficient conversion of gas into stars. The result is that the mean depletion time is quite similar in the centers of galaxies with or without a bar, but the scatter is significantly larger for barred galaxies. This is in logarithmic scale, but in linear scale there is a 4 times larger scatter for the points of barred galaxies. This suggests that the centers of barred galaxies are highly dynamical regions, probably as a result of intermittent gas inflow driven by the bar. Therefore, we see a large scatter in the surface density measured in those centers and also large fluctuations in the observed star formation efficiencies. When we observed the radial distribution of surface densities, we also noticed that spiral arms tend to have slightly higher mean surface densities than the interarm regions at a matched normalized radius, and we can quantify this. If we divide the average surface density in spiral arms, the blue shaded area in this example, by the average surface density in the interarm, the surrounding gray area, we can obtain a spiral arm to interarm contrast. And this is what we get. Indeed, in logarithmic scale, molecular gas and star formation rate surface densities are above zero, which means that surface densities in the spiral arm are actually higher than those in the interarm. However, the long-standing question remains as for whether star formation actually proceeds more efficiently in spiral arms, which would imply shorter depletion times in spirals compared to the interarm. If we take the ratio of the former two quantities, we find that depletion times are indeed sometimes shorter in spiral arms, but definitely not always, with a median ratio of 1.25 in linear scale, which is just slightly higher than unity. And as we can see in this violin plot, many spiral galaxies have interarm values which are actually higher than those in the spiral arms, star formation efficiencies which are actually higher in the interarm than in the matched spirals. As a follow-up, I am now looking into this problem in a little bit more detail, examining not only integrated spiral to interarm contrast, but also their distribution as a function of radius and including a tracer of a stellar mass. In this example, for NGC 1566, we can see the result of overlaying the spiral masks on top of a tracer of stellar mass, molecular gas and star formation rate. And we see that the contrast in arm to interarm is significantly lower in the stellar mass than for molecular gas or star formation rates. If we examine their radial distribution, here for the molecular gas in one arm, molecular gas in the other arm, and now star formation in one arm or another, we see that there are very significant fluctuations with radius. If we take the ratio of the two, we can also see that star formation efficiency fluctuates for both arms, with values above 0 in log scale, implying positive contrasts, above 1 for a radius of 4 to 8 kiloparsec, roughly, whereas for the spiral positions closer to the center or further out, in fact, the interarm is more efficiently converting gas into stars than spiral arms. Therefore, spiral arms pile up gas and star formation, but definitely they do not always result in an enhanced star formation efficiency. To conclude, in PHANGS we are releasing a large set of data publicly, and the environmental masks are not an exception. In addition to the ALMA cubes from MUSE, multiband imaging from HST, and now also JWST for a growing number of galaxies, the morphological masks that I have presented in these talks are also publicly available. So if you are interested in identifying morphological structures in your favorite galaxy, feel free to download the relevant mask from our webpage and use it. It was a pleasure to share these results with you. Thank you very much for watching and stay tuned for more science.